Hey everybody, welcome back. Today's lesson we are continuing on with our look at gravitation, and what we're going to talk about today is this idea that's going to really extend through all parts of physics as we move forward, and we're going to talk about gravitational fields. So really this idea of fields came about when we realized that there are forces and things that can occur between interactions between things that don't require physical contact, right? So if you take two magnets, for example, and you bring them close to each other, they could push and pull and exert forces on each other without actually coming into any physical contact. So we come up with this idea of fields, which basically we define a field as being this property that extends through time and space. So if there's something that you can measure that extends across through time and space, things like mass, like the mass of a rock, it really just belongs to that rock itself. Or if I throw it, the velocity of the rock is a property that it has. It just depends on the rock. So a field is a physical property that is assigned to all points in space and time, which is really just a fancy way of saying that a field is something that has some sort of source and that it extends out from that source in all directions. So if you think, for example, of a campfire, you might think of that campfire as being surrounded by a heat field, that there's this amount of heat that radiates outwards from the central source of the fire. And the strength of that field could vary with different other quantities. For example, as you get closer to the fire, the heat increases. And if we were to build a larger and larger fire, you might also note that the heat increases. And so we'll see this as well anytime we talk about fields, particularly gravitational fields. So fields can either be vector or scalar. Since a gravitational field is a force field, then it is a vector field. And so by that, what we just mean is that, like with all vectors, it's going to have a magnitude, but also a direction. So we sometimes draw, or we always draw, vector fields as arrows because they're vectors. And so, for example, if I wanted to draw the gravitational field surrounding the Earth, that might look like a series of arrows that are pointing towards the center of the Earth, like this. And we can see that in all directions, no matter where you are around the Earth, the field is kind of pointing inwards. So we're already, I should point out that the density of those lines, those field lines, that the more closely packed they are, the stronger the field is. So you can see closer to the Earth, those field lines are a little bit closer together, and imagine further away in space, those field lines would drift further and further apart as you go off. So we actually already know, we've studied this idea of gravitational fields. We just used a different name for it this whole time. And the other name for gravitational field strength is the acceleration due to gravity. So you might think to yourself, well, if I drop a rock somewhere near the surface of the Earth, then that rock is going to accelerate downwards. And that's true, thinking in terms of kinematics and dynamics. But another way to talk about that is to say that, well, the rock itself has mass, and that mass interacts with the gravitational field of the Earth. And because of that interaction, that results in that acceleration downwards. No big surprise that the strength of the Earth's gravitational field is really not going to depend on the object that's in it, right? So the strength of the Earth's gravitational field depends on the size of the Earth, it depends on how close you are to the Earth, but it doesn't depend on the object you put in it. So that's why when you drop a rock or you drop an elephant, they both have the same acceleration due to gravity because they're both being acted upon by the same gravitational field strength at the surface. So you remember that Fg equals mg. So I guess if we wanted to, we could say that g is just Fg divided by m. And if you work that out, then near the surface of the Earth, that'll end up to be about 9.8 meters per second squared. You'll note that the units for this could be meters per second squared, right? Meters per second squared, that's fine for units. But you could also think of it as force divided by mass. So that's just the same thing as a Newton per kilogram. So either of those units will be used interchangeably. The problem is that that is going to be 9.8 near the Earth's surface, but if we want to talk about just anywhere in the universe or around any planet or star or galaxy or whatever, then we have to derive another way of thinking of it. So we know that we know that G is equal to Fg over m. And then we know that Fg is gm1 m2 over r squared, and this is all divided by m. Now, it's worth going back and just thinking about this. What m is this? What m is that? That m right there. Well, that is the mass that is sitting in the field. That's the rock or the elephant that you're dropping. And so if I go back to this formula here, I usually think of m1 as being the mass of the, say, the planet that's generating the field, and m2 is the object that's in that field. So then this mass here is going to cancel out. And what we end up with is an equation for g, which just says g is equal to the gravitational constant times the mass of the object creating the field divided by the radius squared, or the distance from the center of mass squared. Okay? So again, this can be used anywhere. This is universal. So we'll do a couple of examples here, and I would highly recommend, as I always do, and as you sometimes do, pause the video and try these out and see if you can figure them out on your own, and then we'll come back together and get the answer. And so now that you've definitely paused it and you've definitely tried your very best, let's see how it goes. So what is the gravitational field strength on the surface of the moon? Okay, so I've got the moon here. That's the best I can do for my drawing. And I want to know, what is the strength of the field right at the surface? Well, I know the gravitational field strength is gm divided by r squared. So this is going to be 6.67 times 10 to the negative 11 times the mass of the moon, which is given to me there, 7.35 times 10 to the 22, all divided by the radius of the moon to the 6 squared. Now put that all in your calculator, crank it through, and what you'll get is right around 1.62 newtons per kilogram, which again is the same as a meter per second squared. So if you were to drop a rock on the moon, you'd expect it would accelerate downwards at 1.62 meters per second squared. All right, let's try another one here. So a satellite orbits the Earth at a certain radius. What's its orbital period? So here's my Earth. Just gonna draw my satellite. Okay, and I've got the radius. What is its orbital period? Well, the thing to recognize is that if you have a satellite in orbit, as it goes around and around, well, it's moving in circular motion, and so it's undergoing a centripetal acceleration. So the centripetal acceleration, in this case, is equal to, it's just equal to the acceleration due to gravity, or the gravitational field strength. And so I want to find the orbital period. So I'm going to use the format of this centripetal acceleration formula that has period in it. So 4 pi squared r divided by t squared is going to equal gm over r squared. Now, I just need to solve this algebraically for t. I'm just going to point out really quickly here, it would be so tempting. You see how there's an r on this side of the equation and an r on that side of the equation? It'd be so tempting to cancel those out, except that this is in the numerator and that's in the denominator. So actually, when I cross multiply, just take a look, see here. I know you can do some of this faster, but I just want to make a point. So when I cross multiply, I'm going to get 4 pi squared r times r squared is r cubed. On the other side, I'm going to get gmt squared. So that r doesn't cancel out, actually becomes an r cubed. So now solving for period, I'll skip a few steps here, but solving for period, I should get 4 pi squared r cubed all over g times m, and then I need to take the square root of that ugly beast. And when I put in my numbers, 4 pi squared, r is 2.2 times 10 to the 7 cubed, don't forget that, all divided by 6.67 times 10 to the negative 11, and then the mass of Earth, which is, as we all know, 5.98 times 10 to the 24. Crank that all through your calculator, and you should get right around 32,500 seconds for orbital period. Yay, hooray. Okay, so that's it for gravitational fields. Okay, bye.